Okay, perfect. All right. Thanks, Lara and Raul, for this invitation. So I'm going to be talking about the carbon footprint of deep learning. This is something that we also collaborate on and then are interested to look into. And this is a line of research that is currently my core, one of my core research areas on looking at resource efficiency in machine learning. And then taking the carbon footprint angle is like one of the ways we are trying to do this. I would first like to thank, all my collaborators already at the outset who've been, involved in this work at different stages. And then I think we also have like new people who are starting on board, but then most of the work that is presented today, we have like Lesser, Benjamin, Pedram, Eric, Christian, and Nikhil contributing to the ideas. So this is sort of like an overview of today's talk. So I'm just going to motivate a bit and then present one of the main tools of this work, which is called Carbon Tracker for measurement of the carbon footprint, and then some very basic measures on how we could mitigate this. And perhaps that's where it might be interesting to the ROS crowd. So I use this trick, and then I think we've seen this perhaps, but by now we've all tried out, text to image generation models. And then also I asked, ChatGPT to write a poem about robots and AI. I thought that would be topical, and I think it wrote a really long poem. And then I just took a snapshot of some of these lines, and I think it's quite interesting to see what it thinks a robot and AI can do together. So. And both of these are based on these new class of, generative models. One, the image model is called Stable Diffusion, and then ChatGPT is based on GPT-3. Stable Diffusion is trained on 500 million images, and then ChatGPT, the GPT-3 model is also trained on massive amounts of text data requiring huge amounts of compute. So several hundred hours of compute. And in one of our papers, we estimate this to be, if you were to drive a car, then it would be about 700,000 kilometers if you were to drive in a car. So that's the equivalent, carbon footprint of training GPT-3 as a model. So not to take anything away, but the deep learning is quite exciting. There's like lots of interesting research happening here. But I think this whole emphasis on big data and big compute is sort of having like a dent on the reputation, to say, of these methods. Why is that? So before we get into that, I will want to sort of formulate deep learning, because I think it's an important, some of the concepts that we're going to talk, I also assume not many have worked with deep learning, say. So the way I view deep learning is basically as these, class of models, which can take your input X and then map it to an output Y. And they're parameterized by, many trainable parameters, theta here. And X in the Stable Diffusion case could be, you're writing a text prompt, and then Y is the image that you get. Or in the ChatGPT case, it's the query that you write, and then the text response that you get as Y. And the neural network model, the deep learning model, is this F, which is parameterized by these theta. And then, for instance, the number of parameters theta in GPT-3 is about 175 billion parameters. That's like humongous. So, that's where we are getting at. And how do we train these neural networks? So these neural networks are trained using large labeled data sets. And then perhaps in GPT-3 case, it's using a lot of self-supervision, but they are using what is called gradient descent-based optimization schemes. So we want to, get to a model configuration, which can do this mapping from X to Y. But to be able to do that, we have to train these neural network parameters, and then that is using gradient descent. And this is where, a lot of the compute, is involved, because if your theta is 175 billion parameters, and then the number of data points you have is like 500 million images or whatever, so just even parsing through them once to make a gradient update can be quite expensive. So what does this mean? This overparameterization is leading to large compute. Here's a figure from Sevilla et al. From last year, where they kind of categorized deep learning into like 3 eras of deep learning, they call. And then you had like pretty much like a normal doubling of compute, but then after, this is in log scale, And then now more recently, we have these really large scale era where the compute required is not even doubling every 3 months. It's like much more massive. And to be able to, so this is sort of like, Moore's law is not being respected here in any sense. So how do we then take these really large models, which have like 175 billion parameters? Is that even interesting to talk about from like an embedded system, tiny ML or ROS, approach? So what about the carbon footprint itself? Because of this increasing, energy, the compute requirement, so the corresponding energy consumption is also quite high. And why is that? Because there's a direct correlation. So if you want to run large compute, then you also need like large data centers or many more GPU server farms. And then this proportionally increases the energy production. And because energy production is like still a significant contributor to climate change and then greenhouse gases, so this can be a bit of a problematic thing, that because there's so much energy consumption that we need, then we have to be careful about then how much of these big scale compute that we do. Just to put things into perspective, like I already said, the training of GPT-3 model, it can power like 126 homes in Denmark, and Denmark is like an affluent, Western country with the highest standards of living, meaning it's like quite high the energy consumption. So 126 homes for one full year. So that's not a small number. This is how I think that's the message from this slide. So while exciting, I think we should be a bit careful about the energy consumption of deep learning, and I think this is where our work is positioned. And because you cannot, improve what you don't measure. Because if you can train a model, how do you know, what is its energy footprint and carbon, footprint? So that's a bit of a problem for at least a few years ago, that there weren't very easy to use tools to do this. And in this table, we try to summarize some of the tools that are out there, which you can use to, if you are training a deep learning model, to get an idea about what the energy consumption is. For instance, the first tool is a self-reporting one, where you do your experiments and then you go and then fill in a form saying, I ran this particular model for 1 day on this particular hardware in this country. And then it is going to do an emissions calculation and then give you, based on what you reported, the GPU and then, memory cost, the energy consumption. So the other three are basically Python packages that you can install and integrate into your training script so that it can query regularly the hardware and then gives you a more realistic energy consumption picture. And the tool Carbon Tracker is something that we published in 2020, and then it's widely used. We have about 60,000 downloads, and then we allow to not only track but also to predict. Given a setting of neural network training configuration, it also allows you to make a prediction for, okay, what would be the cost if I train this model for this amount of time. And all these tools only focus on this GPU, CPU, and then dynamic RAM. So there's not a lot of overhead that is taken into consideration. And that is, the overhead could be because of the disk reads, and then there's the dissipation costs, and then cooling costs. All of that is usually taken into account using a factor called power usage effectiveness, but I think I will come to it. So just talking about Carbon Tracker, it's a simple tool. It's written in Python. It's under MIT license, so fork away and then do what you want to with it. And you can install it, simply using pip install. And I think that's an easy, that's sort of the easiest access to something in Python right now. And we basically focused on making it as easy as possible, but it's still like, it's not like a graphical user interface or anything, but then it has several supporting platforms, different hardware configurations, but it's still work under progress. And then in the collaboration now with eProsima, we are also trying to give it more features, etc. So just to give you like a peek into what it would look like. So if you have your training or your deep learning code, in here, so it's basically 4 lines of code. So you would import Carbon Tracker. instantiate it. And then here we assume that you're doing like a training, iterative training. So then you would have like maximum number of epochs that you would present. And once that is done, you would embed that into your training script, saying how many epochs, when does the epoch start and end. And at the end of it, you would get an output which looks something like this. So here, for instance, Carbon Tracker has detected what the GPU was, how many CPU cores were there, and then the total carbon emissions for the entire duration. So you get the predicted consumption and then the actual consumption if you do end up running the whole training cycle. And one thing to perhaps notice is that the energy consumption and then the CO2 numbers are like almost comparable. So if you just wanted to get an assessment of what the cost would have been, you can just train the model one epoch and then get this number out. And I think that's one of the use cases we want Carbon Tracker to be used for. And it fetches the carbon intensity numbers live from the local grid, because these experiments were run in Denmark, Copenhagen. So it detects the power grid here to be in Copenhagen, and then fetches the live power intensity. So this is only supported for a few countries now, but it's open source, so it could be integrated and expanded further. So now that we are able to measure these costs, are there like tricks to minimize? Because I think that is where I think it gets more interesting from a tiny ML perspective, where if you want to take these like really large models and then port them into small limited power hardware. So what do we do about that? So one of the things is what we're trying to do right now is look for models which are inherently efficient. So that's because one of if you've trained a neural network, you would know that the search for finding the good architecture configuration is a little like shooting in the dark. So you would start out with like some configuration and then tinker around, or you would do like an expensive grid search over parameters, hyperparameters. So and in most cases, what we end up doing is that if you do um, use energy consumption or just the performance as a measure, you would end up with models which are, extremely power hungry. So they might give you very good performance, but then they also end up having like really high energy costs. So what I think in this work we try to say is like we should maybe look at the energy on this axis or carbon and dice performance, which is like just a performance metric. And you would be interested in model classes which give you like reasonably good performance, because there's not a lot of difference between 0.64 and whatever this number is, right? So it's a small degradation in performance, but if you can reduce the energy cost substantially, then that would be worth investigating. So we took this further and then expanded this into a neural architecture search framework, where you could explore a space of architectures where you're not only trying to get good performance, but you're also trying to do better on the energy consumption in this case. So by doing this, what you would achieve is like a Pareto optimization front, where if you did not care about performance, then you would get like a really low energy model. On the other hand, if you did not care about the energy, then you would get like a very bad performing model. So what we would be interested in is accessing this subspace where you get like good performing models which have like low power energy consumption, or consequently carbon footprint. So yeah, this is just to kind of show that if you did not care about the energy consumption, this is sort of the model that you would get. Whereas if you try to optimize for energy consumption, you immediately can reduce the training time on this axis, number of parameters on this axis, and then energy consumption on the other one, without having any degradation in performance. So on this axis. So, and then because it's Pareto optimization, you can explore different trade-offs, and then you get like other candidate models. So if you wanted to go back to the original optimization of the single objective solution, that is one of the solutions that you would get. And if that's like too complicated, what we suggest is like, we presented these 5 guidelines, what we say, the theta guidelines. So first thing is you want to measure. So when you measure, you want to track, log, and report for controlling and transparency. And then when you do hyperparameter search, don't do grid search, use some smarter strategy like hyperband or Bayesian optimization. And then try to see if your hardware can be, tweaked better or efficient settings. And an intuitive thing was that training location and time is important. So depending on which power grid you're connected to, so the carbon footprint can vary if it is coal powered or if it is wind powered. So I think if you are running job on cloud instances, then making a choice about this would also be useful. And recent frameworks like TensorFlow and PyTorch allow what is called mixed precision training. By default, all weights are in 32-bit precision, but then you can reduce the precision to say 16-bit, and then immediately get like large gains because if you go to half precision, then the energy consumption and then the training time, everything reduced immediately by half. So that's also, like, I think this is generally in the spirit of open science that we should also publish all these training models, which have already been, using quite a bit of data. So I think that's sort of the just general idea with the carbon footprint of deep learning. And I think it's very exciting what deep learning is able to do right now, but we should also be careful about the energy and then the carbon costs. By just immediately adding energy and carbon emissions on another axis, you get access to efficient, architectures. And I think this would be very useful from a research or even from an implementation perspective. There are some tools that exist to measure. I would recommend use Carbon Tracker, but there's also other tools which have other interesting features. So maybe do a benchmarking and then try and use the ones that fit your needs. So if you don't want to, then try and some of the theta guidelines, like automatic mixed precision, immediately reduces some of the energy costs. Yeah, so I think it's just to summarize the same points and try out Carbon Tracker. It's an easy pip install. You can reach me at this mail address or follow me on Twitter or GitHub at Raghavendra. So, thank you.
Okay, Raja. Thank you very much for the talk.
Should I stop presenting? The screen.
You haven't finished, sorry?
Oh no, should I stop sharing the screen? I meant.
Like you prefer is.
Yes.
I don't care. Yeah. No, it's just that it's very interesting, and thank you very much for coming here and for the effort. Mm-hmm.
Okay, I see we won't have any discussions, so we will talk in our meeting next week.
Sure. Next month. Okay. Yes. So thank you very much, Zane.
No problem. I hope, yes, we will talk soon and then catch up on other things. Okay. It's quite late, so have a nice evening.